set.
Good afternoon, everyone. Let me first start by thanking the organizers of this very important Engineer 2D Quantum Materials conference here at ICTS for giving me an opportunity, excellent opportunity to talk about in front of the experts of 2D quantum materials and this very beautiful audience. So for already there have been a lot of discussions happened on two-dimensional electron gas at different perovskite oxide interfaces, especially by Professor D.D. Sharma, Professor Subhankar Chakravarti, and today by Professor Pencheva. But I will be talking about two-dimensional electron gas formed at LVO KTO interface, where LVO corresponds to lanthanum vanadium oxide, LVO3, and KTO corresponds to potassium tantalum oxide, KTO3. So both are actually insulators, but when you join them and make the heterostructure out of it, you get metallicity at the interface. So I will be talking about that. So first, let me thank my experimental collaborators, Professor Subhankar Chakravarti from IISc Mohali, who actually created this LVO KTO interface for the first time and did a lot of measurements on it. I also want to thank Professor Sohan Narasimhan, my advisor from JNCSR, for the theoretical calculations. Now, I will be talking about 2D at heterostructure interface formed between two different materials. For example, you have a material 1, which acts like a substrate material, but now you want to grow another material on top of this layer by layer, and you cannot choose any arbitrary direction of the material 1. So you have to choose those surface direction of the material 1 such that at the interface the lattice mismatch between these two materials will be very, very small, so that you get the epitaxial growth of the material 2 on the material 1. So in that case, people have observed the two-dimensional electron gas formed at the interface between material 2 and material 1. And this electron gas which is forming at the interface, parallel to the interface here, which is extremely confined around the interface region. So this 2D means it is basically a system of free electrons which is confining in the xy plane at the interface, but it cannot go along the third dimension or along the direction perpendicular to the interface. And this confinement of the electron gas leads to the quantization of the energy levels. And the separation between the energy levels is much larger than the thermal energy kBT. So the temperature cannot excite the electrons or cannot lead to the motion of the electrons along the third direction. So this electron gas is really confined around the interface, and thus it gives to the two-dimensional nature of the electron gas. So you can think like that there is a formation of potential well along the third direction, and the electrons are actually bound within that potential. And if you consider the electronic wave functions, the wave functions will be plane waves or delocalized states in the xy plane, but it will be standing waves along the third direction. So the natural question arises that what is the mechanism or what is the origin that you have two insulating materials or two semiconducting materials. When you are trying to join them, you are getting the metallicity at the interface. So clearly this is not the behavior of the individual properties. Okay. So now this 2D research is very, very important, not only for the fundamental physics, but also for the applications. Okay. Already 2D showed many exotic phenomena in 2D, like quantum Hall effect, superconductivity, Wigner crystallization, and many, many more things. And it already had potential existing applications in MOSFETs because of its high carrier density and high carrier mobility. And already 2 Nobel Prizes have been given for in the domain of 2D research. One is in the integer quantum Hall effect, and another is in the fractional quantum Hall effect. Okay, so what I was saying that what is the mechanism that it is not the property of the individual materials, because you have two insulating materials or semiconducting materials. When you are trying to join them, you are getting the metallicity at the interface. So one mechanism is the band gap engineering, which is talked by Gorima Ahuja on 23rd July from our lab, and she has showed that when you have two different materials, and if you know the relative band alignment, which is the position of the valence band maximum and conduction band minimum of these two materials, their band bending happens at the interface. And if you have n-type doping, the Fermi level shifts, move up in the energy and enters into the conduction bands. And as a result, which leads to the formation of 2D, which is sitting from the conduction band minimum up to the Fermi level. Okay, so This band gap engineering, which is basically the combined effect of the band bending, modulation, looping, and gating, can lead to the formation of 2DEC, especially at this kind of interfaces. So there is another mechanism which is which is mainly important for my talk today, which happens at the polar non-polar oxide interfaces. Suppose you have LVO, which is very well known, well studied system, and this has been explained by many people already in this meeting. But so I will cover this very briefly. So if you have LVO, which is a polar material, that means it is consisting of alternatingly charged layers, but the overall the material is charge neutral, and STO, which is consisting of alternatingly neutral layers, if you consider the formal ionic charges. So in that case, your charge density profile will be +1, -1, +1, and so on, and the electric field will be non-negative along the z direction. So if you solve for the Poisson's equation, you will get that the electrostatic potential will increase as the film thickness increases on the substrate. And this increasing of the electrostatic potential or the divergence of the electrostatic potential with the film thickness is known as the polar catastrophe. And this polar catastrophe happens because of the polarization discontinuity of these two materials at the interface. And this polar catastrophe makes the system unstable. But the system has to be stable. So system becomes stable by transferring half electrons from the surface of the LVO to the interface. So these half electrons means half electron per two-dimensional area at the interface. So when this half electrons is transferred to the interface, your new charge density profile will be -1, +1, -1, +1, -1, and so on. So your electric field will not be non-negative, rather it will oscillate about 0 along the z direction. Now your potential will remain finite as you grow as you increase the film thickness on the substrate. So this half electron transfer from the surface to the interface this mechanism is known as the electronic reconstruction. And this electronic reconstruction due to polar catastrophe can cause to the formation of 2DEC, because this half electron which is transferred to the interface now form the 2DEC at the interface. Okay, this is extremely confined around the interface. So this is one another mechanism, electronic reconstruction due to polar catastrophe, which happens and which can lead to the formation of 2DEC at polar, non-polar, or this kind of perovskite oxide interfaces. Now I will actually discuss one early work. There are a lot of materials have been studied in last 2 decades, but the most studied system is the LVO. Okay, in fact, 2DEC first found in LVO in 2004 by Otomo and Huang, when they actually joined two band insulators, very large band gap of 5.6 eV and 3.2 eV. When you join them, they observe the metallicity at the interface. And later people have measured the resistivity as a function of the z coordinates of this heterostructure, and they saw that the resistivity is very high when you are very away from the interface. So in this region, resistivity is very high, in this region, resistivity is very high. But when you are close to the interface, the resistivity drops down few orders of magnitude and gives linear dependence on the temperature, which tells that there is metallic behavior at the interface. And this is extremely confined within 7 nanometer region. So this corresponds to that there is metallic behavior, and not only that, it is actually two-dimensional in nature. So thus it is forming the 2DEC at this interface when two materials are actually band insulators. Now this is the most studied system. Not only in polar non-polar interface, people have also found formation of 2DEC and non-polar interface, for example this material, and polar interfaces also. For example, there are many materials like that. Now in our work, we have our experimental collaborators actually have deposited thin film of LVO on top of the TO2 terminated KTO001 surface. And I just want to mention that LVO is actually a Mott insulator and KTO is actually a band insulator, and both are polar materials. Okay, which is not the case for the LVO, where LVO was polar and the STO was non-polar material. Now one can ask the question that why we have chosen this material. There are a lot of materials available, but we have chosen this material because of several reasons. One of these is that both are polar materials. So the polarization catastrophe or polar catastrophe will happen in both the sides. And as a result, both the surfaces of LVO and KTO will try to donate the half electrons to the interface. So this will also donate, this will also donate. That will increase the electron density at the interface in compared to the polar non-polar LVO-STO interface. So we can expect higher carrier density compared to the polar non-polar. Also in LVO-STO, 2DEC was hosted by TI3D orbitals. But But here we hope that the today will be hosted by tantalum 5D orbitals, which is less localized, or which is more delocalized or less localized compared to the Ti3D orbitals. So you can expect higher mobility of the 2DEG at this interface. Okay. So also there is KTO, which has a very large spin orbit coupling, which is 1 order of magnitude larger than the STO. So you can expect very interesting Rajba physics, but I will not go into this topic today in today's talk. I will mainly cover the results without spin orbit coupling. So these are the aims of the study, which I have already mentioned many reasons. And these are the experiments done in Professor this group from IISc Mohali. And we will actually examine the origin of 2DEG at LVO KTO interface from our theoretical calculations and try to confirm some experimental observations and provide some additional insights. Now, coming to the experimental observations, when the experimentalists deposited monolayer of the LVO, layer by layer growth of the LVO on the KTO substrate, they measured the seed resistivity at the interface. And they saw that when the film thickness is 2 monolayer, LVO film thickness is 2 monolayer, the resistivity is very high. And not only that, it decreases with increasing temperature. That corresponds to the insulating behavior at the interface. So it increases the thickness of the film. So at 3 monolayer, the resistivity drops down, but still it is very high, corresponding to the insulating behavior again. But when they increases the above 3 monolayer film thickness, they saw that the resistivity drops down few orders of magnitude, and not only that, it increases linearly with temperature. So that corresponding to the metallic behavior at the interface. And later, they observed that this metallic behavior is extremely confined within 10 nanometer region around the interface. It is not going very much away from the interface. And they observed the very high mobility, 600, in compared to the polar non-polar, it is higher. And higher carrier density of around 10 to the 14 electrons per semi square, which is 1 order of magnitude larger than the LVO system. Now these are my computational details. So first I will discuss the results of the bulk materials or individual materials. So this is the KTO, which has cubic and non-magnetic at all temperatures. And this is a band insulator. These are the experimental and theoretically calculated values of the lattice constants. And this is orthorhombic LVO, which is a Mott insulator at room temperature. It has the orthorhombic structure. And we have also considered a tetragonal LVO. It does not exist in nature. But we have considered this hypothetical structure because this is the structure LVO takes when it is grown on the KTO substrate. So we wanted to see that, we have chosen this structure because we wanted to see that whether this is the structural transition which is causing the metallicity at the interface or not. So it is due to the structure or it is due to the something else. So we saw that vanadium atoms actually taking A-type antiferromagnetic ordering, and which remains A-type antiferromagnetic when you deposit this material on the KTO substrate. So coming to the electronic structure of the bulk KTO, you can see that there is a clear gap, and the band gap is around 2.2 eV, though it is very small compared to the experimental value because of the use of the GGA, BGGA. And we see that when we calculate the orbital projected density of states, the valence bands are coming from the oxygen 2p with little bit hybridization from the tantalum 5D. But the important thing is this conduction band, which is coming from the tantalum 5D with little hybridization from the oxygen 2p. Okay, so we hope that the 2DEG will be hosted at the interface by this tantalum 5D and oxygen 2p orbitals. Let's see what happens. But remember that this material is insulating. So bulk KTO is insulating. Now coming to the bulk LVO result, which is also insulator, but this is a Mott insulator. Okay, so that means if you do not take care of the strong electron-electron correlation, it emerges as a metal, which is not true. So we have to actually implemented or applied the DFT plus U calculations, and we have seen that with these combinations of U and J, you will get the band gap which matches with the experimental value of 1.1 eV, and you can see that completely filled lower Hubbard band and completely empty upper Hubbard band at this Mott insulator. So bulk LVO is also insulator. Okay. Now I will show the results on the heterostructure interface. So this is the atomistic structure, and this is the KTO part, and this is the LVO part, and we have included some amount of vacuum here. So this is basically a slab model. and we have taken 4 unit cells of LVO on top of the 8.5 unit cells of KTO. And at the interface, you can see that it is TO2 terminated from the KTO side, and it is LVO terminated from the LVO side, which is observed at in the experiment. Okay, so coming to the structural result, polar distortions of LVO KTO interface. So first I want to discuss the related displacement, which is basically at each layer you have a cation and anion, and they got displaced. Okay, so this is basically the jet coordinate difference between the cation and anion, and this is plotted here. You can see for the KTO part at the interface it is negative, and for LVO part it is positive around the interface. It tells that the oxygen anions wants to come closer to the interface, and that creates very little amount of electric dipole in each layer. And these all electric dipoles in each layer point in the same direction. That gives rise to ferroelectric like polar distortion. This is also observed in this kind of similar systems. Now I will show the result of layer resolved PDOS or projected density of states for each layer. Like this is the KTO part and this is the LVO part. So for each layer I will try to show, and let's see what happens. So this is the KTO surface of the KTO. You can see that this is the density of states and as a function of energy, and you can see that the conduction bands is crossing the Fermi level and coming down. So there is formation of free electrons, generation of free electrons, and these free electrons will form 2-dig at the KTO surface. And this 2-dig is sitting from the conduction band minimum up to the Fermi level in this region. Okay, so this is conducting, this layer is conducting. If you go to the next KO layer, this is actually insulating because no states is crossing the Fermi level. So this KO layer is actually insulating. If you go to the next TO2 layer, it is again conducting, but the amount of free electrons has been reduced a lot. So there is large amount of free electrons at this layer, but if you go into the depth of the KTO, the amount of free electrons is reducing very, very rapidly. Okay, so if I go to the next layer, next TO2 layer, so I want to mention that all the KO layers are actually insulating. So I am not showing the results of the KO layers, I am showing only the results of the TO2 layers. So next TO2 layer is actually insulating. Okay, so this conductivity decreases very rapidly, and within 2 layers of TO2, after the 2 layers of TO2, it decayed to 0. So this is insulating. So if you go away from the surface, this region actually acts like the bulk material, and bulk KTO is actually insulating. So you get the insulating behavior here. Like here, this is also insulating. Now, so these middle layers are not important because they are insulator. Now I am coming to the TO2 layer, which is second TO2 layer from the interface, and you can see there is starting of the conduction because the conduction bands move down in energy and cross the Fermi level, and there is small amount of free electrons has been generated at this layer. So this layer contribute to the 2-dig, very little contribution to the 2-dig at the interface. Now coming to the next KO layer is actually conducting. In fact, all the KO layers are conducting, as I told. If you come to the next TO2 layer, which is the interfacial TO2 layer, this is the most important layer because this has the largest contribution to the 2-dig, and 2-dig is sitting from the conduction band minimum up to the Fermi level in this region. And we see not only that, though KTO is non-magnetic material actually, but when you make the heterostructure out of it, you are getting the metallicity at the interface, and this is spin polarized electrons. So you get the spin polarized 2-dig with very high electron density, and these moments in the T atoms comes from the vanadium. So this is kind of induced moment coming from the vanadium to the tantalum at the interface. So this is the most important layer here. And now if I go to the next LVO layer on the LVO side, there is very, very small contribution to the 2-dig. If you go to the next VO2 layer, there is again very, very small contribution. Mainly in this layer, the contribution is coming from vanadium 3D orbitals. So next, after this, if you go, there is starting of the insulating behavior. So this 2-dig is forming in this region only, which is extremely confined around the interface. If you go just away from the interface, it decays very, very rapidly. Okay, so this proves the 2-dimensional nature of this free electron gas. Okay, so again, all the middle layers are insulating. I'm not going. So if you go to the next surface layer of the VO2, LVO, which is very important, you can see that there is valence bands here, which is actually here, which is not crossing the Fermi level. But if you go to the surface, the valence bands are coming and crossing the Fermi level, which corresponds to the formation of holes. So here, here it creates the free holes, and these holes are actually sitting from the Fermi level up to the valence band maximum. So these holes are created because of the lack of electrons, and those electrons actually transfer to the interface, okay, and giving rise to the conductivity. As I explained, that it tries to avoid the polar catastrophe by this transferring electron here. So now I present the result by so here it is. I have calculated the layer result electronic charge by integrating the density of states from the conduction but minimum up to the Fermi level. So this positive is for the electrons and negative is for the holes. And you can see the unit is 10 to the 14 electrons per semi-square. So you can see that largest amount of free electrons are actually sitting on the interfacial TO2 layer, as I showed in the layer result PDOS, and with very small extension on the LVO side and on the KTO side, and this decays very rapidly if you go just away from the interface. On the surface also, and here we see the creation of the holes, as I explained. So these holes are created because the electrons are transferred from the here to here, and that is giving rise to the increment of the electrons here. So this increases the electron density at the interface. So also we see that we compared. So this is the surface part of the KTO. This negative corresponds to the negative integers, corresponds to the KTO part, and positive integers corresponds to the LVO part. So we see that when we compare this surface KTO part with the actual surface, not of the interface, we see that some of the electrons has been transferred from the surface of the KTO to the interface also, and that reduces the amount of electrons at the surface. Okay, so the conclusion is that electrons have transferred from LVO side and from KTO side. I mean, from both the surfaces to the interface, and that giving rise to the very high electron density at the interface and very high localization. So, and I want to mention that the electron density is of the order of 4.89 10 to the power 14, which is very close to the experimental observation, and yeah, and we get the spin polarized 2-deck. So this is the mechanism. You see that 0.35 electrons has been transferred, that corresponds to the creation of holes, and 0.43 electrons has been transferred from the surface, and that leading to the 2-deck formation. And so we see that both the materials being polar, so both the polar materials actually donate the electrons to the interface. So this is the projected band structure, and this is the 2-deck band. I have projected on tandem 5D XY spin up electrons. So this is the 2-deck band, and then I have calculated the effective mass by fitting this band, and I get that this is 0.11 m0, which is much smaller than the much lower than the corresponding LVO system. So this tells that you can get very high mobility. In fact, we have observed in experiment very high mobility of this LVO KTO system compared to the LVO system. And this is because tantalum 5D is more delocalized compared to the TI3D orbitals. So this is the last slide. So I have here calculated the band decomposed charge density, which is basically I have taken the wave function of the parabolic band at the gamma point, and you can see when I do the mod square of that, we see the charge density at the interface, and you can see that the cyan lobes corresponds to the 2-deck. So electrons are actually can freely move in this through these cyan lobes in the XY plane, but they cannot move out of the plane. So this forms the 2-deck. And coming to the conclusion, so we get very thin layer of spin polarized 2-deck formed at the interface between KTO, which is a non-magnetic material, but still we get spin polarized 2-deck, and LVO, which is A-type antiferromagnetic. So this 2-deck has very high electron density and very high mobility because of the lower electron effective mass. And also we see that that the charge or electrons have been donated by both the polar LVO and KTO sides. So thank you for your attention.
And in the 2D, is it isotropic?
Isotropic means?
So you are talking about an effective mass of 0.11, I believe, right?
Okay, so you are saying whether this is this is same in all directions or not?
Yeah.
Okay, actually we found there is very little, I mean 0.1 or 0.14, something like that. So along the gamma x it is 0.11, and along the gamma m it is 0.14.
Because it's very surprising that you're talking about a carrier density which is like E14, right?
Yes.
14 centimeters
14.
squared.
Yep.
And you have and also you have a mobility which is like 600 centimeters square per volt second. Of course that's a low temperature, but still. and so you have an effective mass of like 0.1. So I mean, you're having like pretty large band, like sharp band. So wouldn't it be like density of states bottlenecked with this kind of a small mass, because would it be able to support 10 per 14 per centimeter square
Yeah, so
density?
I mean, you are saying why it is 10 to the power 14?
Yeah, I mean, like, for example, if I compare this with, let's say, standard 3-5 semiconductors, like let us say gallium arsenide,
Yeah, yeah,
the best carrier density you can have is like 5e12 or so, right? And
yeah,
this has an effective mass of like 0.05 or something.
yeah,
And you're talking about 0.1, which is not too far from that,
yeah.
but your carrier density goes up to 10 per 14.
Yeah, so this is
So
because the, as I showed, that the electron, half electrons should be ideally, in ideal case, so half electrons should be transferred from the surface.
I agree with that, but there has to be some states which will support this electron, right? So where is the state coming from? Because it's very sharp band.
Okay, so these electrons which are coming to the interface, that is hosted by the interfacial TO2 bands, especially by TO2 DXY bands.
Maybe we can discuss later. Yeah.
Yeah. So if you integrate this region, you will get of the order of 10 to the power 14 per semi square.
Yeah. Okay. Maybe. So we'll see.
Okay. Yeah.
I just one. Oh, there's one.
Hello. Yeah. So your band gap value theoretically and experimentally almost same.
Band gap value for KTO or LVO?
No, so 1.1.
Yeah, 1.1.
So experimentally, yeah. So band gap match with the experimental value. So did you use any DW approximation or hybrid functional theory? That's
No, I have just used DFT plus U, that on-site Coulomb repulsion and on-site Coulomb exchange. That will help you to shift the this band, lower upper Hubbard band.
okay. So
create
there
the
is no GW approximation or
No, there is no GW calculation.
okay.
Just one short question.
Yeah.
In the experiment, do they see the surface also to be metallic? Because in a lot of other systems, usually we get these. I mean, you have to introduce vacancies,
Yeah.
and then the surface becomes insulated. So that's why I was curious.
Okay, so surface actually in
In
earlier.
your case, you have the surface to be metallic.
Yes, yes. Surface is, yeah. In experiment, I don't know, maybe Professor Subankar Chakraborty can tell in detail, but surface is not Mr. Metallic.
You may
Okay.
have